All right, let's get started with Chapter 11 of Earth Science, Earth History for Finlandia University. If you have any comments or questions about the chapter, feel free to leave them down below, of course. Those of you participating in the live Zoom recording of this, post your comments in chat, etc., etc. We've went over this, but it's still important for me to say it. Cool beans. Let's get going. Chapter 11. Today we'll be discussing all things fresh water, streams, lakes, wetlands, and groundwater. So we're talking water here. We've been slowly transitioning away from rocks and into the other various spheres of the planet that we discussed in Chapter 1, away from the geosphere. Now we're entering the hydrosphere, right? The water cycle. We all know this. We all remember this from way back in the day, right? The movement of water, rain coming down into the lakes and oceans, evaporated back up, forming the clouds, etc., etc., etc. This water cycle, in essence, moves the energy back and forth around by transferring it into different states of matter, liquids, gas, solid, perhaps, if you get into ice, what have you. Notice here at the beginning I said we were going to talk groundwater. Groundwater, as discussed previously, is a very, very small component of the total water on the Earth. The vast, stupidly vast majority of water is sitting in our oceans. About 2.5% of that water is fresh water, and within fresh water, the vast majority of that is ice caps and glaciers, which we're not discussing now. So we're talking about these three here. Sorry, not the atmosphere. We're not talking atmosphere today. We're talking lakes and rivers and groundwater. This little teeny chunk of this massive amount of water. And here's your picture of all the various different water cycle events that can happen, right? Evaporation from the ocean, condensation, precipitation over land or ocean leads to runoff, weathering and erosion, perhaps soil moisture and seepage, etc., what have you. I'm not going to belabor this point too much. I'm sure we've all seen it rain. That's kind of the conversation here. The atmospheric physics of clouds and stuff like that, I believe, is a later chapter in this book. We'll get to that when we get to it. Likewise, it is something that, if you find of interest, find a good documentary on how this works. Clouds are fascinating. Describe the water motion. We all know that. The circle. Everything seems to be very cyclical, right? All right, let's get into specifics here. Let's start with streams. A stream we define as flowing water in a channel. A river is a large stream that's fed by tributaries, and a small stream would be, well, a small stream, maybe perhaps not fed by tributaries. Rivers and streams have a certain flow and velocity to them, given by descriptions such as the gradient and discharge. Gradient is the steepness of the river. The more steep the river is, the faster the water flows, right? Gravity works on it more, I guess. Yeah, that kind of works. Gravity works on it more. Things fall faster down steeper hills, right? Discharge is the amount of water going. You can have a very steep gradient, but if you don't have a lot of water coming out, you're not going to have a very large amount of water flowing by definition. And then we can discuss the channels created by these gradients of discharge in terms of banks and beds. You probably can picture what I'm talking about. I say bank and bed before I get there, but let's get there eventually. What happens when water flows? Well, water and riverbeds are one of the primary sources of erosion, which is something we talked about in previous chapters. That is the movement or transportation of sediments, rocks, minerals, what have you. The competence of the individual streams are the largest particles involved in that erosion. They can be kind of big. You can have rocks tumbling down if the river is fast enough, right? Usually we're talking sediment here, but again, it depends on the gradient and discharge. Capacity is another important thing. The maximum quantity of sediment involved with the motion. Again, large rivers. The Mississippi pours out a lot of sediment. the little stream through the middle of the woods, not falling a whole lot, right? The dissolved load or the ions within the stream flavor the water and again contribute to the same process. Notice here we're decreasing size of carrier material, and we tend to also increase amount. Not a lot of really big particles, fair amount of sediment, a lot of ions, obviously. Certain amounts of the capacity can be suspended in the material. We call that a suspended load. And this is a function of the size and velocity, of course, of the river and the individual sediments. Super finely grained sediments can just sit in the water because the water is moving too fast and it's too turbulent. It has too much buck and flow in the water for the sediment to fall down into the riverbed, hence it's suspended. Or perhaps you have some other minerals that suspend in there by themselves. And of course, we can talk about bed load. Fast, either large particles, large carry, or slow rivers, things eventually fall out of the suspended loads, things eventually fall out of the river stream, and they hit the ground. What happens? Well, these things still tend to move. Rocks, sediment, all that stuff flows along the bottom of the river the same way it does in the middle of the river. This motion, this movement of sediment can cause some sort of down cutting or downward erosion. This is the function of discharge, essentially, and creates a gradient or a bed composition at the bottom of the river. As you move the sediment around, some of it settles, some of it stays settled, more sediment builds on top of that, therefore giving you a riverbed that is built of the sediment that was being transported by the river. Again, this is affected by the amount of water flowing, the speed of it flowing, the types of sediments it grabs, XYZ, blah, 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 blah. It all plays together very well. We've discussed about a lot of different geology and rocks in this class so far. You can imagine all these various components flowing around, causing the vast variety of streams and rivers we have in the world. The base level is essentially as far as a stream can erode. This really gets down most so to sea level. All rivers, all flowing water is going to try to end up at sea level because you can't really get lower than sea level, right? Like sure, lakes and rivers, you can get below sea level. But in terms of rivers, they all want to flow in one direction. Tributaries tend towards rivers because rivers are lower lying. Rivers tend towards the ocean or the sea level because that's lower lying. Not all rivers get to the ocean naturally. Some of them end up in lakes, right? And then, of course, your bed composition can play a factor in this. Sometimes the river is going to hit a harder material and its bedrock as it's eroding. The erosion is going to slow down dramatically. There is a base level to how deep the stream or river can get. And then, of course, we can talk graded streams. A graded stream is when a stream reaches a base level over the course of its gradient. Here we have some really cool examples of kind of what I'm talking about here, right? The river down here has over time eroded all of this down. And we talked a bit about these circular erosions. We talked about weathering and erosion, how those can be constructed. Go back a few chapters if you want to check that out. And yeah, again, this is an example of a lot of very interesting, I would argue, very interesting geology that goes on, right? Take a look at this picture, stop and think about what you're seeing and the massive amounts of time and energy have gone forth to create what we're dealing with here. That looks like something that might not be sandstone. That might be some sort of igneous deposit. Who knows, right? I mean, I could figure it out, but I don't want to right now. Right? We can look at these examples here. What are we looking at? Why is it the way it is? Notice here we've got a lake, right? And then water streaming away from this lake. What's it going towards? This is a gradient amount. This lake here is higher in topography, higher in elevation than this down here. Notice we have some mass wasting going on the side of this mountain. This sediment goes into this lake. That sediment is eventually carried out slowly but surely out here into this river, creating a riverbed, creating a gradient, creating all the wonderful things that we see in nature. Very cool stuff. And yeah, there's a whole story involved with this picture. A lot of very interesting geology, a lot of interesting hydrology going on here, right? This snow, this is fresh water held in, as I said at the beginning, your ice caps and what have you. That's going to melt perhaps when it gets old enough, thereby creating that flow that builds these lakes, builds these rivers, eventually tries to work its way towards the sea. Here we have cartoons explaining these erosion and gradient ideas. At the beginning here, we have a river that broke through somehow and is draining down the course of the hill. Notice at first we have probably waterfalls at the very steep gradients here, lots of damage, lots of excitement going on right here. Slow down river, lots of excitement, slow down river, lots of excitement. And what's happening at these particular locations? At these particular locations, we are getting, as it says here, erosion from the fast water, from the large amounts of water. And then we have deposition where the water slows down again. Right after that waterfall, you're building up. Over time, we can see the bottom picture here. I'll go here. Here we go into better detail. We can see here the deposition appearing as that sandstone, perhaps siltstone, shale, what have you, at the bottom of this gradient. And then give yourself an extended amount of time, things level out. The river will, in fact, erode all of these steps down into something smooth, something natural. But we still, notice here, have these spots where a new deposit exists, a new type of rock exists, and that rock right here and here and here is directly related to the river breaking down, weathering, eroding, what have you, these scarps, these hills here, this topography. This step topography eventually becomes this sloped, this graded, this concave upward topography. And we have evidence of this by the formation of these deposits, right? This river in its current state in this picture is probably a lot slower, a lot less gradient, a lot less speed due to gravity. The water is still coming in, obviously. It's braiding, it's making lakes, what have you, but big difference over time. And that's how streams and rivers work. There is a sinuosity, there we go, sine wave, sinusoid, sine wave, there we go, of stream channels. Meaning there is a flow to them, a back and forth, if you will, as they erode and create the landscape. We have, of course, a lateral erosion or a sideways erosion. Common in low gradient streams, this is the motion of the water laterally or left to right as the water flows, right? We've all been at very tight corners in lakes as shown here. What is this lateral flow? Well, as the water flows around, water is faster on the outside, think outside of a merry-go-round, right? Faster on the outside, thereby picking up more sediment because the velocity of the water is directly related to the amount of sediment it can pick up, and the inside is slower, so you have sediment dropping out of the stream. This is creating motion of this riverbed outward in this direction here, outward, due to erosion of the red and deposition of the yellow. That's what we mean by lateral erosion. This lateral erosion can cause a meandering effect, a seemingly random, although there is reasoning behind travel of the stream. You can get point bars. If you've ever been tubing or something like that on a nice river, you always stop at the point bars and take a break and crack open a nice can of non-alcoholic beverage and enjoy. That is the inside loop of these meandering rivers. Eventually, they get broken off and form yourself some Oxbow Lakes, right? This right here, since you were eroding towards each other, this eventually breaks. The ocean breaks, the stream wants to go straight instead of taking this weird curve, landing you at a lake, what we call an Oxbow Lake. And this is a section of this particular stream. Multiply that by how many sections of stream you got, you can see the path changing, the path developing over time. As shown here, right? Look at this nice sand on the inside of this cut, and there's no sand on the outside of the cut because the river is slowly moving in this direction. I don't know what cardinal direction we're looking at here. The lake is moving out here and depositing sand here. Likewise, it's eroding these parts. You look at this image another, heck, I don't know, 50 years, this may be a straight shot. I don't know if this river is fast enough to do that or not in 50 years. Could be 500 years, for all I know. But you can see this stuff develop and form. And again, go tubing sometime. Tubing's fantastic. Bring your favorite non-alcoholic Jello beverages. You will find the fun of tubing is going around these spots, stopping at these sandbars. They exist everywhere. And then again, this motion carries through to all these splits and divergences and what have you up here. There's a finished off Oxbow Lake. This is exactly what we're talking about, the Flathead River in Montana. This river in the past went all the way around and through here. The river did that. But over time, deposition and erosion caused the river to break off, forming this very characteristic looking lake. This is about as Oxbow Lake looking an Oxbow Lake could be. And then finally, we can talk about some braiding, right? The water's going to go where it wants to go. You've been on the beach, you've poured water out, the water takes whatever path it chooses to take. This tends to happen. You do not have a lot of gradient. There is no preferred one method. Up here, there's a preference. There's a canal, a channel formed where the water goes. Out here, it's flatter. Water can go where it wants to go. Eventually, over time, these channels are going to become, some of them are going to become preferential, and the river, the stream, is going to choose one or another to follow, but that just depends on the velocity, the water flow, and the bedrock it's standing on. Streams, of course, eventually fall into drainage basins and drainage divides. The drainage basin, of course, is an area of land that feeds into a river or stream, and the divide are, well, separate drainage basins. This is a contiguous land that is all downhill, if you will. And the drainage basin depends on the river. Here is a picture of the major rivers of the United States. And we notice a lot of these rivers come in and cut back into one another, right? The Mississippi is the largest river in the United States because of the massive amount of tributaries it has. It's just huge amounts of discharge, right? 14,000 cubic meters per second down here at the bottom. Stupid amounts of water. Colorado River, where the Grand Canyon is, flowing in, the discharges around here, all these various rivers. Again, I'm going to point out here, the big spider in the center, the Mississippi, is the river with the most tributaries, the most connecting points. Therefore, it's going to be the largest because it has the most water coming into it. Up here, the Columbia River, very large, right? Because of, look at all the feeding it's getting. Of course, these streams continuously erode towards the base level along the length over time. You can have uplifting occur, increasing the base level, increasing the gradient, increasing the erosion amounts. The world's constantly in flux, the world's constantly moving. This is a, I believe, rather well understood and accepted idea. A constant dynamic interwork, right? Here's some images showing this process over time. Right, the water originally has rapids to it, a lot of excitement going on. Over time, the excitement of that river is eroded away, giving you a nice meandering river that eventually meanders real hard, creating Oxbow Lake, scroll balls, levees, everything. What do we get from stream deposition? Well, a few big things here. First one is alluvial fans. These are the depositions in dry terrain. You've all seen alluvial fan before. These are big fans of sediment. As the sediment comes down, it travels wherever it wants to. Alluvial fan is created by gravity, right? You've probably seen those before when you take a science classes in high school. The delta is the depositional equivalent in an aqueous or water environment. Mississippi Delta, of course, being the most famous one. It's gigantic. It enters the Gulf of Mexico. You have distributaries within that delta, fans of water channels, and of course, submarine deltas, where the water is deposited as it enters and as it falls out of the river channel into the lake, sea, what have you, it deposits down again, forming this delta. And a Vusian, I think I mispronounced that, is an abandoned stream channel. Eventually, you're going to have these tributaries, get this water coming out. Sometimes streams just aren't preferential for the water to travel through anymore, and they can get abandoned. Animation here of a delta forming. Notice here, the water's just coming in, nice small little point out. Over time, though, since, again, this particular section of the stream is flatter, a bit slower. It's at base level, at sea level, for sake of conversation. The water is going to distribute out, channels out. Get yourself some mouth bars, spread the delta out laterally in all ways, right? And then as you continue growing this, you're going to notice pro-deltas and delta fronts building from that drop of sediments due to the water essentially slowing down, not being able to carry the suspended load as much as it had before. And this is exactly what we see when we look at deltas. You can tell where an old delta was by seeing this delta top, delta front, pro-delta build in the bedrock. Very cool, very interesting stuff. And look at any river that enters a lake, any location, you will see this exact stuff going on, this spreading out. There's usually lots of sand where these things enter depending on the speed of the river, because you have material dropping out. You have sandbars usually near deltas and locations where rivers enter lakes or seas do exactly this point, the deposition of the material as it slows down. Floods, of course, another water event we're all familiar with. A flood happens when more water enters a channel than a channel can hold. You flood the riverbanks, right? There has this natural environments. They just happen over time, but humans play a factor in this as well. We'll get to that. Your floodplain is your low-lying land adjacent to the stream channel. Essentially, the floodplain is what floods. We can try to control flooding as humans by creating artificial levees, artificial channels to either prevent the water from overflowing, essentially making the channel deeper by making it taller, or providing some place for the water to flow if it floods that we prefer, artificial channels, or perhaps diverting some of that water flow. But in the end of the day, right, the flood's going to do what the flood wants to do. You can't predict for everything. Here's an example of a levee as talked about previous. This is a cartoon, obviously, but these are a place you have a large river that is prone to flooding, which is technically any river. People are going to do their best to try to account for the possibility of said flooding. Here we have an example of a artificial levee being built. The natural levees, of course, being the channel cut of the river. And we can tell you can find flood deposits or flood waters that are inundated by low portions of floodplain deposit sediment over time, showing that this area is flooded. And well, we're building houses here. We're not interested in flooding to happen again, so we can build artificial levees, as shown here. The problem with the artificial levee tends to adjust the flow of the waters. The water, as shown here, heightens up as sediment accumulates at the bottom, creating an issue. New Orleans, of course, very famous flood happened some time ago. Lots of conversations about, oh, why you build cities next to flood zones, you shouldn't be surprised when it gets flooded. Well, you kind of hope that doesn't happen, right? Water is a very important factor to life. And yeah, just look at the velocity of the water as it flows through this area. Some places very high, which is over here. Some places very low, some subsidence rates. Yeah, right. This is, I assume flooding is a topic that is, at least at a basic level, pretty well understood by everyone that watches this video. So I'm not going to dive too deep into the concepts, but streams, rivers, flooding all play a big component in it. We can do what we can to prevent it, but at the end of the day, flood's going to flood. Cool. Talk about streams and flooding. Let's go into lakes. Sometimes streams and rivers end up in lakes and not in rivers. Well, how do we define a lake? A lake is a large inland body of standing water occupying a surface depression. Got a hole in the ground, water fills it in, you got yourself a lake. Pond is usually just a colloquial term meaning small lake, right? A puddle is technically a lake if you want to get specific enough about it. Many different common types of lakes include Kettle Lakes. These are lakes caused by initially by blocks of remnant glacial ice. Oxbow Lakes, we discussed already. Volcanic crater lakes. Think back to volcanoes and craters. You can see that connection there. And fault lakes, lakes caused by breakages in the crust due to faulting. They have nutrient balances involved. This is an interesting part about lakes. Since that water is standing, you tend to only get a certain amount of inflow into lakes, and they're small, isolated biomes. They have oligotrophic and eutrophic cycles and the nutrients and in the productivity of the biolife within them. Oligotrophic, I'm mispronouncing, I'm sorry, is your poorly nourished, limited production, since you don't have a lot of stuff for the lake residents to feed on. Your eutrophic is your fish and your algae and your plankton, what have you, are kind of in your bugs or in the wild, having a good time. If you tend to see very blue, clear water, it probably actually means the fish aren't necessarily enjoying themselves too much. Green, water full of lily pods and plant life, what have you, a lot of stuff going on there, a lot of very happy fish, a lot of very happy vegetation. Here we have a nutrient poor lake in the Canadian Banff National Park. This lake has been dammed off by sediment deposited by a glacier and doesn't really have a lot of feed going to it. So this lake is poor biology speaking due to a lack of infusion of other various nutrients and productive parts of the lake, but it is rich in terms of just being gorgeous, having wonderful blue water. These people on this boat and this dock are very lucky. And I mean, look at that picture, just gorgeous, right? Again, good story here, don't we have? There's a lot you could say about this geologically speaking. Here we have a eutrophic lake in Florida. Would I want to swim in this lake? I don't know. Probably not, right? It looks kind of full of mud and sediment. But you know what likes mud and sediment? Plant life, fish life, bug life, reptile life, right? This is a thriving, growing, happy lake to be there. I don't want to swim in it probably, but if I was a fish, I'd much prefer this over this. And I'm not saying this is a dead lake here, by the way. I'm not saying there was no life in this lake. It's just that this lake is not getting, this lake, by evidence of the floor cover, but evidence of just the color of the lake, does not have as much activity as this lake. Lakes within themselves, since they can vary in depth, have some temperature layering and turnover to them. we call that a thermocline, a boundary between warm and cold layers. That's a thermocline. If you've ever been swimming in a isolated off lake like this, you know that the first couple feet of water tend to be the warm stuff. It tends to be the comfortable stuff you swim in. And then when you go down into the dark water, that's where it gets very cold very fast. You pass what's called a thermocline, wherein the heat from the sun doesn't penetrate the water enough to keep it nice and warm, and you get a cold layer, as shown here. Over summer, we have a thermocline. We have a oxygen-rich upper layer, but we are lacking oxygen in the colder layers down below because things can't get down there. Fish ain't going to get down there. You're not going to have the oxygen producing because oxygen everything wants to hang out up top where it's nice and warm. As summer turns into fall, the lake becomes reoxygenated as the heat at the top isn't held anymore. The lake cools down, becomes at more of an equilibrium, and sort of recycles this oxygen from the top. The fish, the algae, what have you, flow around. And then as fall turns to winter, you have a oxygen depletion environment, wherein, let's say you have some ice coverage and you can't get that heat to produce that algae, produce that oxygen, what have you, in the water, oxygen depletion. Of course, over time, spring rolls around, a bit more energy is infused by the sun as the ice melts, algae blooms, what have you. Again, you have this cycle of reheating. You're slowly reheating the lake, and you are getting a flow back to the point to where enough heat rolls in, another thermocline builds. Everything in nature has a cycle to it. The energy cannot be created nor destroyed, merely transferred. So you have this motion in lakes. Again, I'm going to say, if this is a topic that's of interest to you, look it up. Look up thermoclines. Look up energy turnovers in lakes. A lot to happen here. When to fish and where to fish is dictated a lot by this science. Right? This is some practical application to it here, if you're a fisherman. Right, let's move on from lakes, talk about wetlands. What's a wetland? Areas that are wet part of the time have an anaerobic soil and plants that have adapted to periodic flooding. We call those wetlands. Marshes, bogs, swamps, different phrases to mean the same broad category, wetland. Wetlands, of the most common example of the wetland would be the Everglades in Florida. Very, very famous, lots of crocodiles there. You have the fan boats or something like that, I think they're called, that fly around them. Kermit the Frog lives here, if you've ever seen the Muppet movie, right? But wetlands are not exclusive to Florida. Wetlands are, in fact, everywhere, and they're very vital components. We have wetlands up here in the Upper Peninsula of Michigan, if you live around here. Go for a nature walk, find yourself a very moist section, possibly a little bit of standing water along the trail, you found yourself a wetland. It's just that simple. If you don't want to walk into it without waders because your shoes will get muddy, you're probably in a wetland, safe to say. So, notice here we're transitioning speed of water, right? We started out with streams, then went to lakes, moved on to wetlands, now we can talk groundwater. Groundwater is the majority of, well, the second highest majority of freshwater. Glaciers are the first, then groundwater, then your lakes, rivers, streams. And what is groundwater? Well, groundwater is water that's in the ground. Just that simple. It's water that exists in sediment pores, cracks, and fractures. Not all rock and ground has groundwater in it. The most important part of groundwater is the porosity, or how much empty space there is in any particular rock, sediment, what have you. That, because you need space for the water to sit. Porosity should not be confused with permeability, which is the ability for water to flow through the rock. Water tends to, if something is permeable, it's also porous, but a rock being a particular sediment being permeable does not mean it has groundwater, because the whole point of groundwater is that the water sits in the material. That's where the porosity comes from. When we talk about groundwater, we need to discuss the water table. What is the water table? Well, that's the table in which the water sits. It's the flat zone that you get water. You're not just getting bits of water, you're actually getting usable water, right? If you had a well at home, you know that you need to punch the well deep enough to get in past the water table enough to start soaking in the sitting water that exists in the sediment pores, cracks, fractures, what have you. Within the water table, we can discuss a few key points here, such as the zone of saturation. This is the zone where all the pores are filled with water. The ground is saturated with the water. The water table is defined as the top of that zone, where beyond the water table, above the water table, you do not have water in a deep enough concentration to call it groundwater. The rock may be permeable, the water is falling through. The zone of aeration are the porous locations above that water table. Again, your permeability conversation. Water tables have a recharge, or the water that seeps into the saturation zone over time from lakes, from rivers, from rain, what have you. And of course, we can talk about the aquifer. This is the body of porous earth material that can provide useful amounts of water. Aquifers, what's the difference between an aquifer and a zone of saturation? Well, we'll get into that. Picture here shows kind of what we're talking about. Notice we have rain over here on the top of this hill. That rain lands here, and the soil here is permeable, and the water is going to slowly over time fall into and enter this permeable material. Down here, we have the sediment, the sandstone, let's say, the sand, not sandstone, the sediment, that has some water in it. Yeah, by definition of the soil coming down, it's maybe wet, but you're not calling this groundwater. It's kind of just sediment that has water with it. You start to enter groundwater conversation when you get down here to this blue part. Notice all the water that's sitting in the sediment. It's rich, it's deep in water. And if you keep going down, 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 eventually you hit a bedrock that water can't go through, stopping the water from seeping down, giving you a water table. The water table is shown here. That separation between this permeability zone and this porosity, this holding the water versus the water letting through. And in this particular example, we notice that we have a lake or a river over here, and the water doesn't want to sit in the sediment. The water wants to be free. The water wants to be with its buds. So over time, this water table is going to flow into the lake here. It's going to settle in the lake. And if you don't touch it, lake will rise in accordance with this process as the entire water table rises up. Groundwater has a movement to it, or a shape, in which the groundwater mimics the surface with its highs and lows, as shown here. The water table is a certain elevation below the ground, and as such, it flows with the highest part of the water table being on top of the hill, the lower parts of the water table being lower, because the water kind of wants to flow. The water is going to all fall kind of at the same speed, but it has a bottom down here where it can't go any lower. So the water, if the rain lands here, it's going to come down here. In the same amount of time, the rain up here is going to flow down here. Generally, however, inside this picture, the water doesn't want to stay up here. It wants to flow into some place to settle, which is what's going on here. This water is going to be high, but if you have a drought, for example, a long period where you don't have rain, this water table is all going to kind of settle flatter as it goes. Springs exist. These are where the water table intersects the land surface. In this picture, you wouldn't have an example of this. But if this, let's say, was a little valley here, the water table could be below the land surface and water would just spring out of the ground. Perch water table, like this example previous, is water on top of an impermeable layer. Water doesn't go through that bedrock down here, so it sits there. You can have artesian wells, artesian aquifers. I think we have images of that. Here we go. An artesian well, an artesian aquifer comes where you have that impermeable layer, let's say clay shown here, that holds the water at this higher point. The water is pushed out of these springs because all this soil on top of this aquifer is pushing down on it. The water wants to do something, go somewhere, so it spits up the side here. Example shown here of a water spring flowing out of a hillside. Up here, the Upper Peninsula, again, go walking in the woods. You can find springs very readily available, especially if it's just after a rain. When the soil is very saturated with water, it's going to spit out, it's going to make springs. Here we have an example of a confined aquifer that's capable of supporting an artesian well that happens to occur due to the impermeable mudstone separating out the sandstone aquifer. Again, this blue is the water table, so when it rains over here on the left, water is going to flow on the top and noteworthy here on the bottom. And what's happening is you notice over here, this top soil, it follows more or less the flow of the water, but the top edge of the water table in this upper part here rests more or less along with the riverbed. But this bottom layer here, since it's squished, doesn't have anything to level to, that has a water table that's very high. This water table is actually above the topography at the artesian well. This is a natural point where the water wants to leave, giving you an artesian well that pumps up water without you having to do anything. This is due to topography and due to having a lucky break in the layering of the permeable and impermeable layers. The layers with porosity and permeability, and the layers without porosity and without permeability. Right, let's end our conversation of groundwater by talking about caverns, sinkholes, and karst topography. A cavern is, right, a cavity formed by water dissolving soluble rock, a cave, if you will. Sinkholes are what happens when you would say have a cavern and the overlying material of that cavern can't support itself. It's separated too far, so it falls in on itself. And then karst, we'll get into karst as we go, but that is essentially a lot of sinkholes, right? So we have a limestone here. Do we zoom in on these? No, we don't. Okay. We have a limestone here. Limestone has porosity in the form of cracks, more so than porosity in form of sediment. And limestone also reacts with water. So as the water enters, as the rain comes down and enters this limestone, the water is going to percolate through these cracks, through these zones, and simultaneously going to react to the limestone to dissolve it. As you break this down further and further and further, eventually you get a particular crack, like what's shown here, that is big enough and deep enough that the above land can't support itself because there's nothing underneath it, and it collapses down, forming a sinkhole. Eventually, as you keep going here, this limestone is eroded away. The water table is going to fall because the water table only exists based on what water can hold it, right? The water table slowly falls, creating yourself caves, creating deeper sinkholes, right? Over here we have one sinkhole, now we have three sinkholes, creating a cave network essentially. And as time goes, the water table digs deeper and deeper and deeper. Eventually now down here we have an entire cave system built up due to the water eroding away and dissolving the limestone at the base. That's where we get these karst topographies. This is the area underlined by soluble rocks and developed sinkholes and caverns. We call that karst topography. Right here we have karst topography because on top of everything is all these removed away limestone deposits. And of course, once you get a cave, you can have stalactites, stalagmites form, drip curtains, travertine terraces, what have you, based on what the water wants to do with that cave in its current form. Cave networks and stuff like that are more so a result of rock type than anything else. If you have just sandstone, the sandstone will just, the sediment will just hold the water. Permeable and porous materials will just hold the water. A karst or a sinkhole or caverns form when the material reacts with the water, usually. Sweet. Yeah. So there's a couple of questions you want to quiz yourself as you go through this video. All right, coming to the end of our conversation of groundwater now, let's talk about hot springs, geysers, and geothermal energy. We know water exists down below. We know that can be hot down below, depending on if you're close to, let's say, plutons, if you're close to magmatic chambers, what have you. And we know that the deeper you go, the more pressure you get, right? So what happens if you get water, you get it hot, and it's already under pressure, it becomes more pressurized? Sometimes it wants to pop back out of the surface, right? It's going to push its way out because it has to do something. In that case, we can get hot springs and geysers, and if you're lucky enough, geothermal energy. Yellowstone, of course, Old Faithful being a fantastic example of this. Get yourself a vent that is near a heat source down here below, and it's also caved out, if you will, has chambers in it that can hold water, not hold water. You heat this water up, it's got to go someplace. It can vent out as shown here. The heat and pressurization causes the water to expand, right? It's what happens when you heat up water, and it comes bursting out of the top in some sort of gushing effect. Okay. Notice here the water is coming in, filling it up, heats up, squirts out. Individual hot spring and geyser, look at that eruption. Individual hot spring and geyser orientations of the, all right, let me rephrase that. What's underneath Old Faithful is arguably just as interesting as Old Faithful erupting. Knowing the cave dynamics that cause Old Faithful to erupt as often as it does is very intriguing. And it's something that I would argue is worth looking into. Again, kind of bored, not doing a whole lot on your computer, not doing a whole lot on your phone, reading a book, throw out a documentary about Old Faithful and exactly why it erupts when it does. You will thank me. It's a very interesting topic. And there you go. That's groundwater. Not a whole lot to dive into, I would argue. Very vital conversation to have, but groundwater works kind of the way you expect it to work. And again, that's a fundamental concept behind this class. Things work the way you think they work. Geology, hydrology, we get the atmosphere, that can be kind of goofy, but geology, hydrology kind of work the way you think they work. What happens if you got a cave pattern next to a heat source, you fill up that water and you cook it, eventually it explodes out. Exactly what you would imagine would happen. So, thank you for spending your time with me to discuss groundwater for Finlandia University. I hope you got some out of this. If you got any questions, you can shoot me a message, of course. You can just leave a comment, however you want to get to it. I hope this was educational.
Mr. Laird.
Yes.
Hi. Hey, so because I'm in quarantine and I just want to ask you a question. So I already have everything done for my earthquake lab and my plate tectonics.
Sure.
It's just I couldn't get the stuff printed because they got us quarantined still.
Take a picture.
Can I give it to you? I can just send it to you?
Yes. Take a picture with your phone. Send it to me.
Oh, okay. All right, perfect. Then I'll do that. And then also the thing that is it's lab. It's the 240 points thing. It's where we take pictures of like anything we think that's, what is it? You said take 2 pictures of anything around like what happened over the years, right? Is that what it is?
Michael, let me pause the recording real quick and then we can continue this conversation, okay?